This lesson, we will look at implicit differentiation. Just a quick introduction. We are very familiar with explicit functions. That is when the equation is of the form y equal to f of x. In other words, y depends on the value of x. X is our independent variable, y is the dependent variable. Examples of explicit functions, things that you are quite familiar with: polynomial functions, trig hyperbolic functions, more complex functions, and in this case, the first few cases, y depends on x, and that's not necessarily all the time. Here we have s depending on the variable t. So in these cases, the function values, the dependent variables, can be calculated directly from the known dependent values. Hence, differentiation proceeds normally. In other words, we'll use all the standard rules of differentiation: the chain rule, the product rule, the quotient rule, and so on. So what do we mean by implicit functions? Well, these are functions that are difficult to find in terms of the independent variable. Let's have a look at this one. xy squared minus 3y plus 5x is equal to minus 10 does become a bit complicated in trying to make y the subject of the formula. Here we have another. The sine of xy plus 8 is equal to minus 8x. There we can see how x and y are multiplied. It becomes quite difficult mathematically to make y the subject of the formula. Now, such equations are difficult to be expressed in terms of x, and they are known as implicit equations. In other words, the y that you see there could be any particular function. So that y could be a polynomial, an exponential, a Lin function, sine, trig functions, and so on. So when you view implicit equations, try and see y as being a function which you do not know directly. So how do we go about differentiating the implicit terms? Let's look at the very basic ones. So here we're considering y to be some function of x, that is, y is equal to f of x. So if we, in the first one, if we want to differentiate y, that will be pretty straightforward. We can use the syntax dy dx, or y prime, or any of the others that we're familiar with. So whenever we differentiate y in implicit functions, we will immediately write dy dx. Let's have a look at number 2. d by dx of y to the fourth. Find the derivative of y to the power 4. Now recall that that y that you see there is some function of x. So what is this derivative? Well, first I use the power rule. 4y cubed which you're familiar with, but then I don't stop there, because that y is a function of x. In other words, I have to proceed as if I am using the chain rule. Now, to give you an equivalent scenario, consider this function 5x squared plus 3 to the power of 4. That is very similar to y to the 4. If we view y as being 5x squared plus 3, so if I want to find the derivative of 5x squared plus 3 to the power 4, I'm going to use the chain rule. First, I multiply by the index, and I am acting on the argument 5x squared plus 3, which does not change. I subtract 1 from the index. So similarly, the derivative with respect to x will be 4y cubed. Again, if we see 5x squared plus 3 as being the y. But now, do we stop there? No, we don't. I then have to differentiate inside that bracket, and the derivative of 5x squared will be 10x. So I have to multiply by 10x. So that is my y, and then this is the derivative of that y. And hence, when I differentiate y to the 4, I follow the normal power rule followed by the chain rule. The derivative of y is dy dx. Now here I have chosen 5x squared plus 3. That could be any particular function. However, you do not know it. So in this case, number 2, looking on the left, I do not stop there. I follow that through by saying the derivative of y is dy dx. So in number 2 again, that was the explanation for number 2. The derivative with respect to x, notice with respect to x of y to the power 4 is 4y cubed times dy dx. Let's look at number 3. Once again, we are differentiating with respect to x, and y is a function of x. So we're going to use the chain rule here. First, we differentiate e to the y. What's the derivative of e to the y? That's simply e to y. Do we stop there? No. Multiplied by the derivative of y, which is dy dx. These are basic procedures that you have to follow when differentiating implicit functions. Have a look at number 4. U is equal to the ln of y. Then what is du dx? Well, it will be equal to, firstly, 1 over y. Do we stop there? Not at all. Times dy dx. Now that we've come across with logarithmic differentiation. Right, let's go on to some examples, something that is extremely important when differentiating implicit functions. When you get a problem and you notice immediately that you have to differentiate implicitly, I want you to first try and identify a product. Now look carefully at both 5.1 and 5.2. In 5.1, we do have a product. There's 2x cubed and there's y squared. So we are going to use the product rule in this case. Now I'm going to use the FG notation. So I'm going to make F 2x cubed and G y squared. So differentiating using our product rule, I know that that's going to be f prime g plus f g prime. Applying that rule to our product, the derivative of 2x cubed. So I've used that 2x cubed to be f and y squared as g. The derivative of f is 6x squared. Leave the y squared. But of course we don't stop there now. Plus, now I'll leave my 2x cubed and differentiate y squared correctly. That will be 2y. Do we stop there? Not at all. Times dy dx. That is the use of the product rule. Extremely important to identify that you must use the product rule. The only thing that we can really do here is multiply this out, so that 6x squared y squared 2 times 2, that will give me 4 x cubed y times dy dx. We'll come across that at a later stage again when we do more examples. Let's look at 5.2. d by dx of the sine of x squared y. So I want to differentiate sine of x squared y. Now, according to our chain rule, first I will differentiate sine, and then I will differentiate x squared y. However, x squared y is a product in itself. So when I get to differentiate this term, I must use the product rule. So let's go ahead with this. Using the chain rule, what's the derivative of sine? That is cos, and because it's acting on x squared y, I do not change that. Do I stop there? No. Now I multiply by x squared y, the derivative of x squared y, which is implicit, and therefore use the product rule. So looking on the right-hand side, if I get x squared and y, I'm going to make x squared my f and y the g, and use the product rule, differentiate f, I'll get 2x, I'll leave g, plus, now leave the x squared and differentiate y, and what is the derivative of y? That is correct, dy dx. Nothing much that we can really do there. Sorry, that was it. 2x, y. Right, nothing much that we can really do over there. We could multiply the back of it, but I want to leave that. I merely want to emphasize the product rule. Okay, let's go on to examples. Example number 1. Find dy dx if 3x squared plus y squared minus 5xy, 5x plus y is equal to 2. Okay, do you realize and see, pretty difficult to make y the subject of the formula. So how do we proceed? Implicit equations. To help you, first identify whether we have a product rule. Do we have a product rule here? Do we have x's and y's next to each other as a product? No, we don't. So in this case, no product rule. So this should be fairly straightforward. So what's my solution? Differentiate each term separately. Derivative of 3x squared, 6x. Derivative of y squared, an implicit term, 2y, followed by the derivative of y. In this case, I'm going to use y prime. just so that you can get used to the notation. Minus the derivative of minus 5x, minus 5 plus y, the derivative of y prime, that will be equal to the derivative of 2, which is 0. What do we do next? Well, we want to find dy dx. So I'm going to leave the terms that have the derivative y prime on the left-hand side. I'm going to transpose all other terms that do not contain the derivative to the right-hand side, and in simple school mathematics, remove y prime as a common factor, you're left with 2y plus 1, that's equal to 5 minus 6x, and divide through now by this entire bracket to generate the derivative. Y prime is 5 minus 6x. Divide that by 2y plus 1. There you have your derivative. Example 2. Differentiate y sine x equal to x cubed plus cos y. Again, very difficult to make y the subject of the formula, so definitely implicit, but do we have a product? Is x and y together? There you go. There's a y times a sine x. So yes, we do have a product. We're going to use the product rule in this case. So our solution. The first term, y sine of x, using our product rule. Let's differentiate y, and that's just dy dx. Now you leave sine of x, and with the product rule, do you stop there? Not at all. Plus, now you leave the y, differentiate sine x to get cos x, equal to differentiate the right-hand side, that is 3x squared, there's no y there, plus, what about this? First, it's the cos, derivative of cos y minus sine y. Don't stop there because you still have the y, so like the chain rule, you've done the cos, that gives you minus sine y times the derivative of y, which is dy dx. And now I'm going to leave you to do the simple transposition. I'm going to remove the common factor, dy dx. I'm left with sine of x, and when I bring the minus sine y over, that will be plus sine of y. All other terms that do not contain dy dx, I've taken to the right-hand side, so it's 3x squared minus y cos of x. Now divide through by that entire bracket. Dy dx is equal to 3x squared minus y cos of x. Divide through by sine of x plus sine of y. Right, let's go on to the next example. Example number 3. Find the gradient of the tangent to the folium of Descartes. What is the equation? X cubed plus y cubed equal to 6xy at the point 3, 3. Now, the reason I actually taken this is to give you an idea. Remember that that equation contains x and y. Therefore, it can be plotted on the Cartesian plane. Now, we are used to the boring graphs that we've done from school, and we continued here with the first few months at university, the parabola, the exponential graph, the hyperbolas, the shifting, and so on. But these get a little bit more interesting. I'm just going to give you a quick idea, try to give you an idea of what the sketch looks like, the rough sketch after plotting points individually. The folium of this Descartes looks something like this, comes down, turns around, loops, and continues. That is the folium of Descartes, if that's the correct pronunciation. Right, the solution. If we want to find the gradient of the tangent line, we have to find the derivative, dy dx. So I want to derive the equation x cubed plus y cubed equal to 6xy. Very difficult to make y the subject of the formula. What do I use? Implicit. What do I look for? First, a product. Do you see a product? Yes, you do. X times y. So yes, we do have the product. Let's differentiate. The derivative of x cubed, 3x squared. Derivative of y cubed, 3y squared, times dy dx. By now you should be thinking along those lines fluently. Now here, the product rule. I'm going to take 6x as the first factor, y as the second factor. So the derivative of 6x is 6, leave the y, plus, now leave 6x, times the derivative of y, which is dy dx. Once again, do the transposition. I'm removing dy dx as the common factor. I'm left with 3y squared. I'll have to transpose the 6x. That becomes a minus 6x. All other terms remain on the right-hand side or are transposed to the right-hand side. That gives me 6y minus 3x squared. And then divide through by your bracket, dy dx, 6y minus 3x squared, divide by 3y squared minus 6x. Now at this stage it's quite okay, it's fine for you to simplify, take out a common factor, but no temptation, no cancelling of x or y's at this point in time. However, I need to find the derivative at the point 3, 3. So notice I have the ordered pair. That's my x, that's my y. X is 3, y is 3. Therefore, my derivative will be mere substitution into the answer. 6 times 3, 3 times 2 squared. Divide that by 3 times 3 squared minus 6 times 3. Working it out gives me an answer of minus 1. That completes that example. Right, let's look at the next equation. However, this one contains higher order derivatives. How do we go about finding derivative of a derivative of implicit functions? Well, let's take this example. Obviously, we must first find the first derivative. And again, this is an implicit function. So let's differentiate to get our first derivative. That's 4x cubed, 4y cubed, sorry, times dy dx. That gives you 0. Derivative of 16 is 0. Now at this stage, we can continue with the differentiation, or we can find the first derivative directly. So transposing, I get minus 4x cubed, and then divide by 4y cubed gives me an answer minus x cubed over y cubed. So that is my first derivative. Now, to find my second derivative, and I'm just going to try and use notation so that you get used to notation. My second derivative is the derivative with respect to x of the first derivative, which is minus x cubed over y cubed. And again, if we're differentiating any function that contains x and y together, that's implicitly. Now, how do we differentiate this? I'm pretty sure you've noticed the quotient rule. So applying the quotient rule now, the denominator, y cubed, must be squared. The numerator, y cubed, derivative of the denominator, of the numerator, I beg your pardon, 3x squared, minus, now I leave the numerator, which is minus x cubed. I've chosen the numerator to be a minus x cubed, times the derivative of the denominator. And the derivative of y cubed is 3y squared. Do you stop there? Not at all. Times dy dx. Now we need to simplify. However, notice that dy dx, we have actually worked it out. So I'm going to do that substitution. Let's simplify wherever we can. The numerator, I can multiply 3x squared y cubed. Negative comes a negative for the minus x cubed. 3x cubed y squared. And now we can replace dy dx by minus x cubed over y cubed. And that, of course, is all divided by y to the power 6. I'll continue with the problem here. That is equal to, can we simplify further? Yes. In the numerator, the first term remains the same, minus 3x squared y cubed. The second term, we can cancel off y squared with y cubed, and then watch the sign. And x cubed times x cubed, that gives me 6, so that will be 3x to the 6. Divide that by y, and that is all divided by y to the power 6. And now I can multiply both numerator and denominator by y, because y over y is equal to 1. And I multiply in the numerator every single term by y. So y times minus 3x squared y to the 4th is minus 3x squared y to the 4th. 3x to the 6 over y's cancel off, minus 3x to the power 6. And at the bottom, y to the 6 times y to the power 7. Can this be simplified in any way? Yes, it can. I can remove -3 x squared as a common factor. Let's see what happens. Y to the 4th remains, plus, now remove 3x squared from there, x to the power 4. Divide that all by y to the power 7. But do you notice something? Look at this numerator. Y to the 4th plus x to the 4th. Look at the original problem. Find d2y dx squared if x to the 4th plus y to the 4th is 16. So this is simply 16. Substituted into there, I get -3x squared times 16 over y to the power 7, giving me my final answer, -48 x squared over y to the power 7. That completes the examples on implicit equations.